The outline of my talk will be a little introduction, infrared lasers and infrared detector, and future and conclusion. The past, present, and future of lasers and detector is in the difference atom in periodic table. If I take the atom of hydrogen, thanks to quantum mechanics, we know that electron can absorb the photon, go to the higher energy level, and emit the photon to come to the initial energy level. That is the basic of the absorption and detection and emission. The wavelength of this photon is proportional to the Planck's constant, speed of light, and the energy between the initial and final level. By changing the difference atom in the periodic table, I can make the lasers and detector from deep UV up to terahertz. So if I take only the part of the periodic table 3-5 semiconductor, the column 3 and column 5, by atomic and gap engineering of this element, I can make from the interband, inter-subband to make all of the different lasers from, again, deep UV up to terahertz. And important of these 3-5 are, they are covalent bonding, they have direct energy gap, and at the same time, they have most of them zinc band structure. So it's excellent for the semiconductor, lasers, and at the same time, detector. So in the past, we had bulk material. And with the bulk of these 3-5 semiconductor, we couldn't go far from having the infrared laser and detector. In present time, we are using the quantum mechanics, superlattice, very advanced epitaxial growth, and we can make the lasers and detector, again, from the deep UV up to terahertz, and still there are some gaps that we need to fill up for the future. What is the future at this time is if we use quantum mechanics and to go to the low dimensional, 2-dimensional confinement, 3-dimensional confinement, quantum wire, quantum dots. In this case, we can make the quantum infrared lasers and detector much more efficient and independent, again, of the temperature. So for that, again, if I come from the periodic table, going first to the difference element of the aluminum, gallium, indium, and nitrogen, and we can see here that from this material, I can go from the deep UV up to terahertz, and with the inter-subband up to terahertz. So what is the problem here? One of the problem is the substrate. So that's the future that we have to solve it. And on the other hand, again, with this material, I can come the allophonon in this material is more than 90 electron volt, milli-electron volt, opposite to the indium arsenide, gallium arsenide that we are using at the present time for the infrared detector, in infrared lasers. So if we use the III-Nitride, we can solve some of the problem that we cannot solve with the other 3-5. It means that we can come up with the room temperature at the same time, not only the laser, but to have to fill up some of the gap that we cannot fill with the indium phosphate or gallium arsenide by using the gallium aluminum nitride, gallium nitride inter-subband. And here we demonstrated that we can have up to 5 micron, and we can go at the same time to have up to the 50, 60 micron, and even up to terahertz. So for that, there are 2 elements that we have to solve because we have not the substrate. One is we have to have the resonance tunneling and the transport. That is the basic of again, to have the infrared laser and detector. So we did some demonstration here, but need, again, that's the future to continue. Now, we tried to demonstrate it from the 1993, all of with the world first demonstration of some of the devices that is possible with the III-Nitride, but at the same time, that is the time for the continuation, for the improvement up to terahertz. Now, if I come to the visible part, because the eyes can see only from the 400 to 700 nanometers, or more than 700, it becomes infrared. So if I come for the 808, 980, that is very important again for the difference application, especially telecommunication, that we had gallium arsenide, gallium aluminum arsenide, MBE. We change it to the quaternary aluminum free with the MOCVD, and that we demonstrated that yes, that can revolutionize to have much higher power, much cheaper, much better performance, but is not finished at this time. We need to use this material again for the monolithic integration with the silicon and with the difference again, the active and passive devices. So that's the future. Now, if we come to the 1.3, 1.5 micron again, gallium indium oxide phosphate, indium phosphate for the telecommunication, that again, we demonstrated that LPE is not a best solution, MOCVD, and at the same time demonstrated that now we have for the future, the things that we need, again, we have to come much better again, performance of the, not only the reactor, that the precursor. We have to be very careful with the indium phosphate, because for the phosphorus, as an example, we have only one source of the phosphine in the world at this time. So all of from the material, from the source, from the reactor has to be optimized. And now that we demonstrated on the silicon, and that is again, that's the future, that we need to have the integration of all of the passive active device based on the 1.3, 1.5 on silicon substrate. So that is the future again. Now we are coming to the longer wavelength infrared from the 2 micron up to again THz, up to THz again. We have here, I put 3 micron because there is a gap again at this time from the 1.7 to 3 micron that needs to be filled up with the high power, high performance continuous wave, again the lasers. And at the same time, application, they are numerous, so there is a huge need for the future. So what we can do, we know that already, that we have interband, and at the same time, for to go to the higher, we have inter-subband. That again, that is started by in 1970 by Razeghi and Su, that they gave the ideas of the superlatives and negative differential resistance, and they demonstrated mini-band and sequential tunneling transport. And after that, it was Kazarinov and Suri that they took again the ideas and to demonstrate that it's possible to use it for the by photon assisted tunneling, to use it for the infrared laser. And it took long time to demonstrate, yes, that is possible to have the infrared high power at the same time, the lasers, by doing the molecular gas source molecular epitaxy and controlling the material. We demonstrated, yes, it's possible to use that and to have high power continuous wave from the 3 to 12 micron. We demonstrated, and after that it comes now the difference group is coming, but again there are still the gap that has to be filled up to THz. And now we need at the same time high power, high ball plug efficiency, continuous wave, room temperature for the difference wavelength, for the difference application. So for that, we already demonstrated for the first time the 40-watt photonic crystal distributed feedback at 4.4 micron. That still is the unique, still is the highest, and the record, but unfortunately it's very difficult to make. But we came with another solution to show that they brought the beta DFP with the design, that very simple way. We try to demonstrate we can have up to 203 watts with the single mode far field, single mode electric at room temperature, but with the high performance. But that is again is a demonstration, needs not to follow up, and this difference group can go and to go at the same time to the continuous wave. So we need the monolithic widely tunable the infrared. The things that we did in the telecom part, now we need in the infrared from the short wavelength, mid, long wavelength. And for that, we try to come with the monolithic widely tunable QCL between 6 to 10 micron. And we demonstrate at the same time a kind of the friendly, compact and user-friendly system around this source that can go very the scan, the rapid scan up to 1 kilohertz, but for the random wavelength. But that is the demonstration. We need now a lot of effort for the continuation, but for the continuation for the different kind of application. So that is again is the future trend. Now we need photonic integrated the circuit, similar to the electronic. We need the monolithic steering with the surface emitting in the QCL for the different wavelength. So we again for the first time, we demonstrated that it's possible to put all of the different components in the same chip and to demonstrate very high, about the 17.9 degree the tuning, and we demonstrated that is very fast with the 3 dB bandwidth of 7.75 kilohertz, and the output beam is a very, very narrow, but again, all of that is the demonstration, not it needs to be followed and to continue for the future. Now we need silicon photonic. We need that everything again on the same substrate and to have the much higher power again. That we demonstrated here. That is the world's highest long wavelength infrared continuous wave power phase locked arrays that we have 8.2 watts with the wall plug efficiency of 9.5% at room temperature, 1.8 kiloampere, and the very nice again performance at the same time. That is the spectral width that very, very narrow 1.2 nanometer, and at the same time the far field peak is a 0.25 and is the limit of the system, and the very no. So all of that's a demonstration now is going for the future for the different application. So now for the THz, we know that application of the THz for the different health, security, the remote sensing, communication, everything. But what is missing? Missing is the diode lasers that we can use it similar to one that we use in the infrared or in the visible. So for that, again, we came to demonstrate there is a possibility with the DFG to have the performance, the room temperature THz emitter with we demonstrate up to 1.2 to 2 milliwatt with a very nice far field, and at the same time the continuous wave, and we demonstrated with the tuning. But unfortunately, again, that is only the demonstration, needs not to be continue, and for to make it high power, high continuous wave at room temperature for the different application. Now for the frequency comb, again, we know the application of the frequency comb, and we got the Nobel Prize, and we know that the problem of the not to have the frequency comb at infrared up to THz. For that, again, we demonstrated even that at the THz, we can have room temperature the frequency comb that is working. So all of that is the demonstration and needs again to continue for the future. Now, coming in the case of the lasers, starting from 1997, we demonstrated up to now many different applications, many different record, and many different spheres. So that all of that it was the demonstration, now needs to continue now. Now, coming to the detector part. In the detector part, application of the infrared detector is very, very important because human wants to see infrared that we cannot see. We cannot. Nature didn't give us to do that. So for that, here we have the semiconductor again, the photodetector research from deep UV up to THz, coming from the again, intrinsic material coming from the quantum well, quantum dots, and at the center, that is narrowband, and the top two, that is the broadband. So for that, again, for that, I would like to come first to use the quantum dots. Exactly as I mentioned, that is the future. Quantum dots, quantum fire. But what has that? We did that. At this present time, we have the quantum well infrared photodetector. But unfortunately, if we go to the quantum dots and quantum wire that we demonstrated, we can have much better performance, much higher focal the energy, the quantum efficiency, and at the same time, we can have much better independent of the temperature coming to the higher the operating temperature. But unfortunately, that is narrowband. In order to go to the broadband again, we came with the solution of the 3-5 semiconductor, because mercury cadmium telluride, it was the thing everybody was working. But when I came again to US, I started by the 3-5 from the indium antimonide. Here we have energy gap as function of lattice parameter, indium antimonide base, and all of that you can see is changed again, revolutionized the world of the infrared imaging that I can see, showed you here, that aluminum antimonide, gallium antimonide, indium oxide, this material and this band gap energy is again studied by Razeghi and 1917, but up to 2003, nobody in the world could make the focal planaries with. And that, if you can see here, the ETBM theory show that is the gamma is a center of brilliant zone by using the indium oxide gallium antimonide wide band gap material, by doing atomic and gap engineering, one monolayer chain. As you can see, you can change the gap, and by that again you can see that here by ETBM you can have the difference again, the parameter to optimize and to have the any wavelength that you want with the excellent performance of the lasers. And that we did, and we tried to demonstrate for the first time in the world, yes, that is possible in mid wavelength, in long wavelength, and that after that they came to say that on the two color. Why? Because if you have only one band, you can see only that. The second band, you can see only that. But if you have the two together, you can see much better performance. So we tried to demonstrate, yes, it's possible to have the two color again. And we did that, the world first demonstration again, long, in 13 micron, 9.5 micron, with the excellent performance, and everything is done at university in the inside with the student, that each student transferred the technology at this time in US, and they are doing great. And now coming to the short, mid, long, because you said that, look at the difference. Here you have 13 micron, 5.3 micron in the same device, and look at the difference that you can see. So now, coming to have, again, with the same material, we need to go broadband. It goes even into the short wavelength. That is important for the NASA. So about atomic and gap engineering, you can see that we can change the gap by 1-2 monolayer aluminum antimonide to increase, and by that to have the active passive, and to have the world first again to color the active and passive. Passive, it means that is a thermal, and active, you need light. So that you can see again for the first time is demonstrated. And that now we are going to have one of the problem that we have is the following, because the material for the production, they had the problem to say that is very hard in order to make this system. So we came with another system. It means that indium oxide antimonide, exactly as you can see here. And by changing again with the gap engineering, we can have again not only to come with the different wavelength, but at the same time to come with the barrier to have the material that can go from the 0.5 the micron visible the UV up to the terrace with the excellent performance. And exactly as you can see here, how by doing the atomic gap engineering of the 3-5, we can again change the gap for as an example, for the 9 micron, by putting a little barrier, we can go to the 1.8 micron or even less than that. So now, another thing, again, the three color. Why? Because our eyes has the three colors. We know that. If you have only one band, it's not, and two band, again, and if you have the three, you can have much better performance. That is for the different application. And we demonstrated, yes, that is possible, again, with this material to go from deep UV up to THz for the multicolor. So, conclusion here again, 1970 is demonstrated by Razeghi, this material, and it took up to 2003 that for the first time in my group, we demonstrated the focal planaries, because nobody could do that. But we did. And after that, we demonstrated all of that one after each other. And we educated the student that they came and they learned and they tried and transferred the technology to the industry. Now, if I come here at the same time, what was the revolution of the talk too that is changed again in the space lab, and at this time is started to use in the space. And you have to know that when at the same time, at the beginning, when I was telling, everybody was fond of me and nobody wanted to believe, but exactly as the result came out, and at the same time, the technology transferred through the excellent student. That is that. So in conclusion, for the detector part again, I came for the first 1993, starting by the 3.5 of the indium antimonide, indium thallium antimonide, bismuth antimonide, and up to now, and all of that they are one demonstration that did most of them only in my group, and that's the future that we have to continue, and I hope that NSF can help in order that that can be continue for the future. So what does the future hold? Again, inspiration comes from nature. Fundamentally, nature operates in quantum level and is full of wondrous use of the quantum technology. We have studied quantum well, but nature is not limited to a single degree of confinement. Going forward, we can go more quantum, go to the quantum wire, quantum dots, and two-dimensional, three-dimensional, and at the same time to put everything like the VLSI on the same wafer, on the same, as an example, silicon, and to use. So we need, again, exactly as I mentioned, for the infrared lasers and detector, the 3.5 semiconductor, that is the best, again, but we need a lot to work on that to make it, again, much better and much more efficient. Okay, thanks.